Hello guys, today I'm going to solve this problem from Leetcode's June challenge. This is third problem, and the problem statement says that there are two n people a company is planning to interview, and the cost of flying the ith person to city A is some cost, and cost of flying this ith person to city B is this much. We need to determine the minimum cost to fly every person to city such that exactly n people arrive in each city. So we are always given a equal an even number of people, and we want to fly all of them to either city A or city B, minimizing the overall cost of flying them, and with the condition that each city should have exactly n people. So there might be scenario that a person is closer to city A, but in the best case it is possible to send him into city B even if it is the distance for him to city A is closer than city B, because the city A has already all the other n people, and we won't send him to city A. So yeah, I have already solved this. Let me explain you my approach, and then I'll walk you through the code. So the simplest idea that comes to our mind in this case is that we can try to simply we can compare the cost of, let's say, this person, then we'll compare the cost for this guy to go to this city, and compare this to this city, and then choose this one, choose the smaller one for this one. This should, let's say here the cost is 10, and here if the cost is 20, we would try to go greedy and choose 10 for this one. And then we decided to send this person to city A. But what could happen because of this person going into city A? The population of city A has increased, like the length of this the size of city A, the number of candidates for city A has increased. So this is a very important factor. How? Let's see. At any moment later, let's say we have filled all these position, all this seat for the city A. We have exhausted the threshold, the quota that we had. For each box we had n people as the limit. So let's say at any moment we have exhausted all the this limit for A, and now this guy, it has 800 very less amount, let's say 1 for city A, and let's say 1000, which is very big, or the biggest of all of them, for city B. So if we would take a look, by making a sacrifice at any point earlier, we would have gained a very very good amount of cost. Like, instead of sending this guy to city B, we could have sent it to city A instead, and yeah, just by not going greedy at every step. So this shows that the greedy approach might not be the most efficient one in all cases. So how shall we approach this? So the other approach is the dynamic programming based approach. But before that, I would like to try to explain how can we try to solve this recursively, and then we can try to see the subproblems and overlapping subproblems and try to memoize that. Let's take this example. We have city A and B and 6 people, and we want to, let's say, make a decision on this guy, for example. So we would either send it to this city or this particular city. Then what are we going to do? We are going to let's say consider both of these possibilities, like send this particular person to city A and city B. So what's more important here is which particular person we are talking about, and we also want to consider one more param, that is the current length. We can keep length of one city because they are going to be distributed in half. So if we would know in the end that let's say if we have distributed all of them, then we can simply in the end check if this length of city A is equals to n by 2 or not. If it is n by 2, then it is a valid case, and that means we have distributed. If this is not n by 2, that means it's not a valid case. And so what are we going to do? We are going to compare the answers from all invalid and valid cases, so whichever gives us the best result. So for all the invalid case, we would try to send the maximum result, so that maximum possible result, that means positive plus infinity, so that when compared with some valid results, it would automatically be ignored. And then so yeah, that's what our state should look like at each particular state. For each particular guy ID, let's call it ID, and we are going to just make a decision whether this guy should go to city A or city B. If he is going to city A, and this length is describing the city for the length for city A, then the next state should look like idx plus 1. That means id plus 1 for the, we should then consider the next person in the queue. And if this is going for the city A, then this should be len plus 1, and this answer should be added to the cost of the next guy, the cost of this person to fly to city A. So we would add this cost, let's say cost A for id. And otherwise, if this was case 1, and for the case 2, we can have like id plus 1, like consider the next person by sending this guy to B, city B. And if we are sending this guy to city B, then we don't increase the length of city A, like the number of people in the city A. And then this answer should be, then the next then the answer should be added with the cost of sending this person to city B. So these are the two cases that we will compare, and we'll compare the best result out of these two. So now, as we have seen that we can solve it recursively, trying out all the options that we have for each person, let's see if this problem can be solved by using dynamic programming approach or not. So what dynamic programming approach asks for, that the problem should be having subproblems, like if we want to solve the problem, the bigger problem, can we break it down into smaller subproblems, so that the results of the smaller subproblems are going to help us find the answer for the bigger one. And also if these smaller subproblems are overlapping or not. So let's say in our case, the problem is we have certain f function, f of id and length at any moment, and what we want to do, we want to calculate the answer for all these people if we consider this particular function. So what do we want to say? We want to say what's the most optimized answer if we start from this id and this length already filled for city A. These many we need to consider all the people ahead from id. Let's say in the beginning it will be 0, and initially we have 0 people filled, like there are 0 people for city A. Then the answer for this one lies into two things. If we are able to find the answer from city 1, like say person starting if we are able to find the answer for all the people starting from 1, and let's say with 0 people still in city 1, and then the answer from all the people starting from id 1, and total 1 people currently in city 1. And then once we have find the answer for both of these possibilities, we are just going to add the cost of having this possibility and cost of having this possibility. That means cost of person I, that means cost of person 0 flying to city 0 and cost of person 0 flying to city 1. We add these two sub problem solutions that we have, and then we'll compare both of these results, and then we'll choose the minimum one. And this is what we are going to do for 1 and 0 as well. So now that we have seen that at any moment any problem can be broken down into certain number of subproblems, and then we try to find the best answer out of these subproblems, and then we find the answer for the bigger problem. Now let's see how if they are overlapping or not. So if we take a look here, let me just bring it back. Yeah, so I have drawn this decision tree. So we started with 0 0 0 0 tells us that we are currently considering all the people starting from 0, that and we have selected 0% for city A. Then what we can do, we can choose this person city for city 1, and then we can city 0, and then we can increase both of them and find the answer starting from starting from ID 1 and with 1 people in city 0. I will say city 1 in city A and city B instead. So we chose to go city A, and here we chose to go city B. And if we chose to go city B, then we will consider the answer for all the people starting from ID 1, and yeah, we didn't increase the size of people in city A. So similarly here, if you can see, so basically what I'm trying to tell here is, in this decision tree you can see there are multiple problems which would be called multiple times, like for example 2 1 here and 2 1 here. Also if you see, yeah, because 2 1 and 2 1 are same, so all these children are also will be same. Similarly 3 1 is matching here. So yeah, it seems like we are calculating multiple problems every time, so they are somehow they are related. So basically we can see that if we can just store the result for one of the subproblem, we can use it for the other subproblem. So like these two seems to be overlapping in that case, they too have similar problem. So basically 1 1 and 1 0 has certain subproblems which are same for both of them. So in case if we have found the answer for one of the subproblem, we can use it for the other one. So that's what we are going to do. We are going to build the recursion, and then we are going to memoize the answer for one subproblem that we have already calculated, and then if we see the same subproblem again, we will use this subproblem, the answer for this particular already calculated subproblem to this in this case the new smaller subproblem. So let's see, with all these ideas in mind, how we can code it. So here is my solution. I'm going to explain you how can we implement this. So I have declared one size of the total people and the cost array globally, so that we can access it in our function. Also I have declared one DP table which should be of size 100 cost 100, and yeah, 100 for the size for the number of people, and 100 can be for the at max length in one particular city. Also the base case is that if I reach the end, that means there are no more people, then I'll check if the number of people in this city A, that means the length should be equals to the overall size, half of the overall size. If that's the case, I don't need to add any more cost, I have already calculated. And if that's not the case, that means it's an invalid case, and I should return the maximal possible answer from here. In this particular step, I'm checking if this subproblem is already calculated or not. If that is already calculated, I have marked it -1 if it is not calculated. But if it is calculated, I would return the answer from previously calculated value. And otherwise, as I have shown you, that we have two options. The first option is that we will include it into city A. That means the city A size will increase by 1, and we will add the cost for choosing this person into city A. Otherwise, we would choose the other option. That means we will send it to city B, and in that case the size of the city A will not increase, and we will add the cost of sending this person to city B. And then what we are going to do is we are checking out the answers for both of them recursively, and also once we find the answer we will store it into our DP table. And here, as you can see, I've just initialized my DP table, assigned the global cost to the local cost vector here, vector of vectors, and then also assign the size. Then I have started from 0 0 0, and that will bring us the answer. Let's submit. So yeah, it went through. So yeah, I hope that I was able to explain this with all the sub problems and the decision tree, how this is not a greedy, what are the problems with the greedy approach and all. Please let me know if you have any comments or doubts for this in the comment section below, and hit the like button and subscribe to my channel if you haven't already for other videos similar for similar problems. So thanks for watching this video, guys, again.